Hello everyone, and thanks for listening to this presentation of our article, Transciphering using FiLIP and TFHE for an efficient delegation of computation. I've worked on this research during an internship at Thales with Thomas Ricosset from Thales and Pierrick M from the UCL, Université Catholique de Louvain. First, a bit of context. Say you have some data and you want to compute a function of them, but you want to delegate this computation because it is heavy and you want a server to do it. However, you don't trust this server. You know he is honest but curious, which means he won't perform any unwanted operations on the data you send him, but he will look into them. The cryptographic solution for this scenario is an homomorphic encryption scheme. The idea is that you can encrypt your data with such a scheme, send them encrypted to the server. The server will perform operations on the encrypted data, will send you back the result, and when decrypting it, you will have the function, the evaluation of the function you wanted. There are different degrees for homomorphic encryption scheme. The schemes can be somewhat homomorphic, or leveled homomorphic, or fully homomorphic. Fully homomorphic is the best one, in the sense that it allows to perform any operation on your encrypted data, and it has been achieved in 2009 by Craig Gentry. Since then, there has been many fully homomorphic schemes, and they can be gathered in 3 generations. The main issue with homomorphic encryption schemes is that they are heavy, in the sense that the ciphertext weighs more, encryption and decryption takes more time than with regular encryption schemes. The main idea of transciphering is to reduce the amount of computation and the usage of bandwidth client-side. So let's say the client is a small device who cannot perform homomorphic encryption. It will just have to perform a light symmetric encryption scheme, send the symmetric cipher to the servers. The server will then be able, using an homomorphic encryption of the symmetric key, to perform transciphering, which means to transform the symmetric cipher into an homomorphic one. To do so, you will have to homomorphically evaluate the symmetric decryption function. Our main contribution is the implementation in C language of a transciphering. This is the first time a transciphering was implemented using third-generation homomorphic encryption schemes, and we try to use the characteristics of the third generation to perform more efficient transciphering. In the transciphering protocol, there are 2 schemes. So first, we will introduce the TFHE scheme and the leveled homomorphic scheme we implemented. Then in the second time, we'll talk about the stream cipher symmetric scheme FiLIP and how to efficiently homomorphically evaluate it. Finally, I will present our results and compare them with other transcipherings, like for example, second generation homomorphic ones. TFHE stands for Torus Fully Homomorphic Encryption, because all the computations are performed over the real torus, which is basically the reals modulo 1. We can also define a polynomial structure over this torus with a standard negacyclic polynomial ring. We also have a notation for binaries and for binary polynomials that we'll use through this presentation. TFHE schemes rely on the learning with errors over the torus problem. Learning with error is a very common problem that is used in many lattice-based schemes. The idea behind it is pretty simple. If you have a secret vector S and are given public vectors A and the scalar product with S, if you have enough public vectors A, you can retrieve S. It's equivalent to solving a linear system. So you just perform Gaussian elimination and blah, blah, blah. However, if you just add a little bit of noise in each of your scalar products, retrieving S becomes an hard problem, and this is the learning with errors problem. It exists in different versions. So the one I just presented is the third version when we try to retrieve S. There is also the decision version, where you just have to distinguish between a uniform distribution or a distribution coming from a learning with error sampler. There is also a ring version where your scalar product is replaced by a convolution product between polynomials. All those problems are equivalent. We can define an encryption scheme that relies directly on the LWE problem. So one described here is used by TFHE for the fully homomorphic scheme. You take a message from a message space, which is a discrete subset of the interval 0, 1. The key is just a binary vector. And with this message, you just create an LWE sample. You add your message with the error. To retrieve the message, you just take the last term of your ciphertext. You subtract the inner product to this last term. You end up with the message plus the error, and you get rid of the error by rounding up to the closest element of your message space. What is important to note is that there is noise in the messages, in the ciphertext, which means that if the noise gets too important, you lose the message information. TFHE also defines TLWE samples that are basically LWE samples with polynomials. So we can note that there are two-dimension parameters, the dimension of the vector and the degree of the polynomials. If the dimension of the vector is 1, then TLWE relies directly on LWE. If the degree of the polynomial is 1, then they collapse to their constant coefficient, and the underlying problem becomes binary LWE. LWE-based schemes are naturally additive, which means that if you sum two ciphertexts, you get a ciphertext of the sum of the messages. However, there is a noise growth during the operation, and we need to remain careful that we keep the correctness of the scheme. Now we have an homomorphic addition, but we still cannot perform product, and we need both addition and multiplication to perform any operation we like and to evaluate FiLIP. That's why we need to introduce a bigger object, which is TGSW sample. So a TGSW sample is a matrix, and to get it, you just take a matrix where each line is a TLWE sample of 0, and you add your message encoded with what's called a gadget matrix. Using TGSW samples, we can perform external product. So it's called external because it's an operation between TGSW sample and TLWE samples. The details of this operation include a decomposition using the gadget matrix, which gives the basis. But what is important is that at the end, we get a TLWE sample encoding the product of the messages. So it gives us an homomorphic multiplication. Using the TFHE tools that I've described, we were able to implement a leveled homomorphic scheme. This scheme encrypts binary messages as TGSW ciphertext. So we chose to have TGSW ciphers because it was important that at the end, after the transciphering, the server could still perform any operation on the homomorphic ciphers it got. If we chose to remain in TLWE, we've seen that we don't have a product between TLWE ciphers. The binary messages choice comes from the fact that when you perform multiplication, the plain text norm appears in the error formula, and we want the error to remain small so that we can make multiple multiplications, and that's why we have small messages. The scheme in itself is pretty straightforward. Basically, to encode a message, we just create a TGSW sample of this message, and in order to retrieve the message, we use a well-chosen line of our ciphertext, which gives us a TLWE cipher, and when we decrypt this TLWE cipher, we can retrieve the message. With our scheme, we have a native homomorphic addition. We just sum ciphertext in order to get the ciphertext of the sum of the messages. Examining the noise growth during operation. Since the noise generated is random, there are several ways of examining the noise growth during homomorphic operation. we can look into the worst case scenario or an average case scenario. One of the contributions of TFHE is that it allows to look average case scenario, which gives more tight bounds, and that's what we did for our study. So the evolution of the noise during homomorphic addition is linear. We also have an homomorphic product by defining an internal product, which is easy to define using the external product introduced earlier. The error growth during the multiplication is a bit trickier, so we won't give the formula, but what is important to note is that it is asymmetric, which means the noise of A dot B is not the same as the one of B dot A, so it is important when we implement it to put our operand in the right way. And also, the noise depends on the plain text value. So multiplication by a cipher of 0 won't give the same noise as a multiplication by a cipher of 1. Both those properties, in third generation, allows to perform a lot of multiplication. Now that we have our homomorphic encryption scheme, we need a stream cipher. So this figure explains how FiLIP works. Basically, there is a totally public PRNG, the seed is public, everything is public, and a key register. With the PRNG, you'll start by taking a subset of the key. Then you'll shuffle this subset, and finally, you'll XOR random bits from the PRNG to this shuffle. All this operation can be easily performed homomorphically. Actually, if the key register is ciphers instead of just regular bits, you can perform all this operation without adding any noise. Just taking a subset and shuffling and adding known values isn't really a homomorphic operation. It does not take time, it does not add noise. But after you've done all that, you have to pass the filter, from which comes the security of the scheme. So a filter is a Boolean function, and it outputs one bit, which will be our stream cipher bit. In this work, we consider two families of filter, and I will present both of them right now. So the first one is TSM filters. TSM stands for direct sum of monomials. So it's basically a Boolean function where each variable appears once and only once, and it's a sum of product. It can be represented by a direct sum vector. There is an example in the slide, and it's pretty straightforward. Since it's just sum and product, it's easy to homomorphically evaluate. You just compute your sum and your product, as you will do with plain text. So DSM filters we used for implementation have around 1,200 variables, and they can be evaluated with as many homomorphic operations. The second family of filters we used are XOR mash filters. So XOR mash Boolean function is just the sum of a XOR function and a mash function. XOR function just outputs the sum of its variables, the XOR of its variables. And the mash is a majority function. So it outputs 1 if at least half of its entry is 1, and 0 if not. The one we use is a function with 144 variables. It can seem less than DSM function, but XOR mash functions are a bit trickier to evaluate homomorphically. We don't have time to get into the details, but it can be used using a decision circuit with MUX, and in homomorphic evaluation, when you do evaluation condition circuit, you always have to look into every condition, because you can't really know the value of the data you are manipulating, so you can't do real conditions themselves. So at the end, it takes about as much computation to homomorphically evaluate a 144 variables XOR mash function than a 1000 and so DSM function. Since we know the functions we want to homomorphically evaluate, we needed to choose the parameters for homomorphic scheme. These parameters must fulfill two requirements. First, they must grant enough security, so 128-bit security. To evaluate the security given by our parameters, we use an LWE hardness estimator. Secondly, these parameters must guarantee that we can correctly evaluate our filter, which means that the noise will not overflow during the homomorphic operations. We require that at any time, the probability of decryption failure for ciphertext remains under 2 power minus 128, if this requirement is not fulfilled, it can lead to attacks. With all that in mind, we made a noise evolution model and ended up with two sets of parameters. The performances of our implementations are given in the following table, so for the different set of parameters and for the different filters I've introduced. The data we use to evaluate our performances as the latency and the key size. First, the key size is just the memory size of the symmetric key server-side, and the latency is the time needed to output the first bit. So in the case of FiLIP, since it's a stream cipher, latency is the same than throughput. It means basically that we can transcipher one bit every approximately 2 seconds. We also implemented another scheme, which is a mix between TGSW and TLWE scheme. The idea is the encrypted symmetric key is still TGSW ciphers, but at the beginning of the filter evaluation, we transform the first TGSW cipher into a TLW1 of the same message, and then we can perform external product all the way of the evaluation of a cipher. So it leads to a faster filter evaluation, since the external product is faster than the internal one, and smaller ciphertext, because the ciphertext becomes TLWE ones. But that's also the problem, because with a TLWE cipher, we cannot perform homomorphic multiplication, so the resulting homomorphic cipher is not totally usable by the server. It needs to perform a bootstrapping and transform it into another cipher to use another scheme. So we can see the performance gain in the following table. It is a table that compares different versions of FiLIP. In this one, you can find the basic TGSW scheme, the mixed TGSW TLWE scheme, which is around 2 times faster, but also a TFHE scheme. So for this one, we just implemented Transciphering using the TFHE library as it was intended to be used, with fully homomorphic operation, but it's way slower. And also a previous version of FiLIP with second generation homomorphic library. We also compared our implementation performances with existing transcipherings. We ended up with a good latency. However, our throughput was slower than most of others transcipherings. This is because they use patching, which means that in a single ciphertext they can pack several messages. The downside of this technique is that your ciphertext become linked. You cannot perform operation between two plain texts that are encrypted in the same ciphertext. To conclude, in this work, we implemented for the first time a transciphering using third generation homomorphic encryption. We also implemented new filters for FiLIP, because in the previous implementation only DSM filters were implemented. We ended up with good latency. We could still improve the throughput by batching our messages. Our homomorphic scheme could accept binary polynomial as messages. If we manage to do so, we would gain a factor 1000 for the throughput, with the downsides I've talked about just earlier. Another improvement will be to be able to bootstrap the resulting cipher, because it will allow to perform an unlimited number of operations on the data server side. Thanks for your attention.